We started the lesson by motivating the idea that we want to be able to use calculus to answer questions about the optimal way of doing something, the best solution to a problem, the most cost-effective way of manufacturing we can, and so forth. But a byproduct of the work we need to get to optimization problems gives us a lot of information about curve sketching. So we will spend a little bit of time understanding how the big superstar in this chapter, which is the mean value theorem. Let me say that again, the big superstar, which is the mean value theorem. Real big superstar. Like it has a permanent place on the test. Or perhaps across many questions. What implications that has on curve sketching. So, when we look at a graph of a general function, we'd like to identify the parts of this graph and break it up into two pieces in general. What I mean by that is we want to talk about the parts of this function that are increasing and the parts of this function that are decreasing. And so, when I ask that, when I say that, we're always thinking from left to right. That's our convention. So from left to right, where is this function increasing? And we can identify that. It's not very difficult. Okay. It's increasing in this region, right? And it's increasing there. So I'm going to say increasing here, and in this region, it's decreasing. Now, why could it be important to identify those regions? Because the parts that separate the regions of increase and decrease, something very special happens there. You could get a peak or a valley. And these were called local maxima and minima, respectively. So, our first consequence of the mean value theorem today is going to help us identify the intervals on the x-axis for which the function is increasing, and the intervals on the x-axis for which the function is decreasing. So we'll start with that result, and then we'll see an example of how it's used. So here's the corollary. We're going to start with a continuous function on the closed interval AB, and the same function is differentiable on the open interval AB. And that makes sense because if this is a consequence of the mean value theorem, then the conditions on f must be at least the same as those of the mean value theorem. This corollary has two parts. First part says, if the derivative of this function is strictly positive at every point of AB, okay, then the function is increasing on that interval. Part 2 says something very similar. Would anybody like to venture a guess? We'll start with the same language. If very good. So if f prime is less than 0 at every point AB, then f is decreasing on that interval. Okay. The reason I want to do the proof is because it will help you solve the first problem on the homework. Okay? The first problem on the homework proof is very similar to the argument I'm going to make here. You'd have to tweak it a little bit, but it's the same idea. Well, I kept on saying this is the consequence of the mean value theorem, so we're obviously going to use that. And it's easy for us to see how that's valid, is because the conditions are like they should be. But let's go back to this picture for a moment here, and I want to prove part one. Let's just take two random points in an increasing portion of the graph. Let's call this first one the x-coordinate having x1 and the second one x2, with x1 less than x2. Yes? What can you say about the function values? This is the function value at x1, and this is the function value at x2. F of x1 is less than f of x2 if x1 is less than x2. Does that make sense? Mm-hmm. Okay. So that's the way I'm going to prove it. I'm going to let x1 and x2 be such that one is less than the other, be in the interval. Okay? And my goal is to do some clever things and end up with f of x1 less than f of x2. This is my goal, right? If I can argue this, starting here and ending here, then I would have shown that the function is increasing. So this is a proof of part one, which assumes that f prime of x is greater than 0 for all x between a and b. Okay. Consider the function f on the interval x1, x2. The closed interval x1, x2, which is contained in AB. And apply the mean value theorem. Are we able to apply it? Is the function continuous on this closed interval? Okay, because it's within this, right? And it's differentiable on the open interval. So to apply the mean value theorem, well, the consequence of the mean value theorem is that there exists a number c within the open interval x1, x2, such that what? F prime of c equals f of x2 minus f of x1 over x2 minus x1. Yes? Now, we're going to end up with an inequality, right? Yeah. So the idea is, okay, so we have this situation. Could I argue that one of these quantities satisfies some inequality based on the hypothesis here? Can I argue that this satisfies some inequality? Is this greater or less than some number? Greater than what? 0. This is greater than 0, yes? Yeah. In fact, f prime of x is more than 0 for any x, so in particular for this special number c, the derivative is positive. So I could say that this quantity is positive. Yes? Yeah. But surely the denominator is positive. Do you know why? Because we set it up that way. x1 less than x2. So the difference between x2 and x1 in that order is positive, right? Okay. So if the denominator is positive, the only way this fraction can be positive is if the numerator is also positive, right? So this forces the numerator to be positive. that make sense? Again, we know the denominator is positive. The only way a fraction can be positive with the positive denominator is if the numerator is positive as well. Yes? Okay. Okay. So we wrote that down. This is the numerator, and we put that as positive. And that implies that f of x2 is greater than f of x1, which was our goal. In other words, if I go from left to right, from a smaller number, smaller x to a larger x, the function value gets larger than the function value before it. And that means, so that's what our goal was, right? That means the function is increasing in that interval. The proof of part 2 is symmetric to this. Okay? Very symmetric. What that means is you could write down the same proof and change some inequality symbols around, and you'd have a proof of part 2. Yeah?
This is for like numbers that are on the same function, right? Like if,
Yeah.
so
We're talking about one function increasing from left to right.
if it's two functions, is it going to be the same way?
Like for the question in the homework?
Um,
No. It's going to be similar. And maybe if we have time at the end, I'll talk about that question. Okay? But the idea is, if you want to prove, all you have to take from this is that we're using the mean value theorem, and in order to prove that one quantity is greater or less than another quantity, then you have to show that the difference is positive or the difference is negative. Right? In other words, if I have two numbers, alpha minus beta, so that their difference is negative, what do you conclude from that? Alpha is less than beta. Right? So, in the homework, you're expected to show that one number is less than another number. And if you go back one step, that just means that the difference in the correct order is negative. And that's going to come, that negative is going to come from the derivative. And that's how the mean value theorem plays. That's all I'll say about that one. Let's do an example to use this to a specific function. So, find the intervals over which this function f of x equals x cubed minus 12x minus 5 increase, decrease. So this is kind of the idea. We have some curve. We want to find, we're going to say, between these two x's the function increases, between these two x's the function decreases, etc. And that's what we're trying to find, those intervals for which that's true. Well, according to this, the intervals of increase and decrease depend on f prime. So we're going to start by calculating f prime. So f prime is 3x squared minus 12. Yes?
yes.
Okay. So, that's continuous, yes?
Mm-hmm.
Yes. Therefore, to find out where it changes sign, right, you'd have to find out where it's 0 first. In other words, you're looking for the critical numbers. So find out where f prime equals 0, or doesn't exist. Well, f prime always exists, so the only way f prime will be 0 if x equals negative 2 or 2. If you solve that equation. Now, the domain of this function is all real numbers. And the derivative is 0 only at 2 points. That naturally gives us, if this was the x-axis, and we have to consider the whole x-axis because the domain is all real numbers, these two critical numbers fall here and here. And that naturally divides our real domain into three parts. The part before -2, the part between -2 and 2, and the part after 2. And we know that if there would be a sign change for f prime, it would only happen within these three parts. In other words, if we pick a point here and the derivative happens to be positive, we're guaranteed that the derivative is positive throughout that region. And if we were to pick a point here and get the sign of f prime at that point, then we know for sure that within that region, f prime will preserve that sign. There are no sign changes within these individual regions. Okay? We can take some test points. So the test point before -2 might be -3. And then evaluate the function, the derivative of that function here. So if I evaluate -3, I get a negative number. So f prime is negative in that region. Oh, positive. Sorry. And then if you pick a number here, perhaps 0 is a good test value, and plug it in here, you get negative. And if you take a test value, perhaps 3, and then you get a positive number. So if I were to write this down in words, I'd say that f prime is positive on which region? Negative infinity, -2. Union 2 infinity. So on this region, the function f prime is positive. And f prime is negative on the interval -2 and 2. Okay. But that doesn't answer our question. But it sets it up. It sets it up so that we can use this corollary. Because this corollary says if I know that f prime is positive on some region, like for example this one, then I know that f increases in that region. So my conclusion is that f increases on this region, and f decreases on this region. Okay? I promised that we would talk about curve sketching. Well, this gives you a little idea of how the curve behaves. So you know that in this region it's going to increase, in this region it's going to decrease, in this region it's going to increase again. So although you've never plotted individual points, you have some information about the general shape of the graph. Okay? Now, based on this general shape that I just sketched over here, and what I mentioned earlier, is that if a function is increasing up to a point, and right after that point it decreases, then there's a special point there, there's a local maximum, right? Okay, well, what is so special about that point where the function increases and then decreases in terms of f double prime? It changes sign, right? From positive to negative. And what's so special about this point? It's a local min. And it so happens that f prime changes from negative to positive at that point. Okay? Okay, so this is stated formally as the first derivative test. For local extrema. Okay, I should make a very important clarification now. The word first is not about the first test. It's that this test involves the first derivative. Okay? So it's not like this is the first test for local extrema. It's a test that involves the first derivative. So take this as one piece over here. Okay? And that's going to be important for what we do for the second derivative test. So here's what the test implies, but we need some conditions on f. So f is continuous on an interval containing C. Okay, so there's some interval, C is in it, and f is continuous throughout that interval. The second condition is that f is differentiable on an interval containing C. And except possibly at C. And I'll explain the second part of this, why we don't need it to be differentiable at C. It may, the test works even if f is not differentiable at C, as long as it's differentiable a little before and a little after. In other words, as long as the function is smooth a little before C and a little after C. So that's the hypothesis, that's the setup for the theorem. And here's the conclusion. You could just probably guess what it is. If f prime changes sign from positive to negative, at C, then f of x has a local maximum at x equals C. In other words, f of C is a local max. If f prime changes sign from negative to positive at C, then f of x has a local limit at x equals C. In other words, f of C is local limit. But there's a third part. And this is going to really distinguish why this is more powerful than the next test that we're going to learn. If f prime does not change sign, at C, then f of x, or let's say it like this, f of C is neither, well, it's not a local extremum. Okay, if there's no sign change, then f of C is neither a local max nor a local min. So this test handles all the possibilities. Okay, you're either going to change sign or you're not. If you are going to change sign, it's either going to be from positive to negative or negative to positive. And that handles all those cases. Okay? So this test, what does it test? Well, you get the critical number, right? We talked about critical numbers last time, and that they are only candidates for local extreme values. That they may not necessarily turn out to be local extreme values. We didn't have the tools at the time to decide. But this test tells us that if I have a critical number I'm sitting on, I know applying this test, helps me decide whether we have a local max or a local min or not at that point. All right? So let's do an example to see this in action. Find the local extreme low of F. So step one would be to find the critical numbers. Find out where f prime is 0 or does not exist. Okay, which means I need to find f prime first. To find the derivative, I might need to use a product rule, which is perhaps not the best thing to do here, because it's not too hard to rewrite this as a difference of two functions. Right? Does that make sense? Yeah. 4. And then doing the derivative now, finding the derivative is much easier. F prime of x is 4/3 x to the 1/3 minus 4/3 x to the minus 2/3. Yes? Okay. So I want to figure out, to find a critical number, so I got to figure out when is this 0 and when does this not exist. Okay? Well, like any other equation, if we could factor this, it would be really easy. Is there a common factor besides 4/3? Well, whenever you have an expression with exponents of x, you pick the lower one, right? X to the negative 2/3. Okay, so this would be x minus 1. Does that make sense? How we factor that? And perhaps now, if we write it this way, then we can answer this question very quickly. The critical numbers that we have, when f prime is 0 and x is 1, and f prime doesn't exist when x is. Okay? Does that make sense? Okay. Now we want to study the sign changes of f prime. We'll start by the domain of f. What's the domain of f? If it's not given, we have to pick the largest possible domain where the function makes sense. Is it R?
No.
We have some cube roots there, right? Okay. So, is there a problem with that? We can use all real numbers? Yeah. If it was square roots, we'd have an issue, but we don't. We have cube roots. We can use all real numbers as the domain of this function. So then, when we're studying the sign changes of f prime, we can consider the whole real line and use the critical numbers to break up this real line into 3 regions. We have the region before 0, the region between 0 and 1, and the region after 1. Again, for the reasons I said earlier, there will be no sign changes in this region alone, or in this region alone, etc. So we pick one test value and see what happens. If x is -1, what is the sign of f prime? From here. If x is -1, the numerator is negative, and the denominator is, well, the denominator is always positive, isn't it? So this is negative. Now, if x is between 0 and 1, take, for example, half, the numerator will be half minus 1 is negative. The denominator, again, is always positive. This is still negative. Okay? All right. And then After 1, take perhaps 2. The numerator is 2 minus 1 is positive, the denominator is positive, so f prime is positive. Okay? So according to the first derivative test, we're going to have a local extreme value if there's a sign change in f prime. Where is there a sign change? At 1. So f of x has a local, now we have to be careful. Okay, so change of sign from negative to positive means f has a local minimum. Local minimum at x equals 1 because f prime changes from negative to positive. Changes sign from negative to positive. Okay? Is that clear? Yeah.
Why is that only cube root and the domain is
Well, you could take cube roots as negative numbers, but you can't take cube root or square roots as negatives. You'd run into complex numbers. Okay. Any questions about this first derivative test? Okay. Now let's combine the two ideas and try to sketch a graph of f. Now, it's always good to try to figure out the intercepts. There's an easy intercept. When you say, from looking here, there are very easy the x-intercepts. What are they? 0 and 4. Okay, so 0, 4. That's all we can get from the function for now. But from f prime, what can you say before 0? The function is decreasing, right? Because f prime is negative. So if the function is decreasing before this point, where does it have to be before this point? Above. So it decreases to it, right? Okay. So it's become like this. And I won't connect it here just yet. Now what's happening between 0 and 1? It's still decreasing. Okay. And then what's happening? It's decreasing until 1, right? Okay, so I have to be careful. Let's say 1 is here. It's decreasing until 1. And then after 1, what's happening? It's increasing. Now, how do we know that this is going to continue going up and not curve back down?
It's never decreasing again.
Very good. It never decreases again. There are no other critical numbers that will change the sign after 1. So we know that, okay, and for that reason, we know that this is never going to curve back down. It's just going to go like this and continue going upwards. Now, it's very important to use the derivative to figure out how we connect this part of the curve to this part of the curve. Because something special happens at 0. So where did 0 come from? That the derivative was undefined. Well, let's see. Let's figure out what the derivative is. If your x is 0 or near 0, let's say x is going to 0 from the left, right? Then what can you tell about the derivative here? The numerator is about -4. What's the denominator? If x is close to 0, the denominator is Are you whispering? Can you say it out loud, please? What is this expression when x is near 0 from the left? 120? Did you say 125?
No. It's an undefined method. No.
Oh, yeah, but what? Negative, positive. What type of number is it? infinity, yes? Is the test comprehensive? This is chapter 2, guys. This is limits. Anyway, so the limit is negative infinity. That just means that we have a vertical tangent line, okay? So when we connect this here, we have to make sure we do it in such a way so that f prime has a vertical tangent at that point, okay? Because there should be, the derivative doesn't exist not because it's sharp, but because we have a vertical tangent line, okay? Okay, anyway, that's the graphic function. Okay? That's pretty much what f prime tells us about the graph f. The next part of the lecture is, what does f double prime tell us about the graph of f? And before I talk about that, I want to go back to the first example I wrote down. I think it was x cubed minus 12x minus 5. And we did a rough sketch of this graph, and we came up with this type of curve, right? I think it was increasing until -2, and then decreasing between -2 and 2, and then increasing after 2. This is -2, this is 2. I don't know where the x-axis is, because I don't know specific values, specific points on this graph, but this is the general shape. Now, something important happens here, about here somewhere. The concavity, whatever that means, changes. In other words, the curve everywhere before this special point is like an N shape, right? And the curve everywhere after this point is like a U shape. And we'd like to figure out if the second derivative says anything about where it's going to be N-shaped or where it's going to be U-shaped. And moreover, where does that change in concavity happen? And that's what we're going to study using the second derivative. So let's be more clear about that N-shaped, U-shaped stuff. Let's write a definition to clarify everything. So, the graph of a function is said to be concave up if all its tangent lines are above it. Okay? And concave down with all its tangent lines are below it. Okay, so going back to this curve, let's sketch some tangent lines to make sense of this definition. So let's pick this point here and draw a tangent line. You see that within that region, the tangent line, well, at that point it's the same height, but beyond that point, in both directions, this pink line is above the curve. Actually, if you do that at any point, you'll see that the tangent line is above the curve. Okay? At any x value, the blue line is below the pink line. At any x value, that's the relationship. So in that area, the function is concave down. Did I write the definition wrong?
Yeah.
Okay. it's nicer this way anyway, with different colors. So here it's concave up because we have the tangent lines at every point in this region are below it. Okay? Now, we said that the second derivative was going to say something about this concavity, but it's not apparent from this definition how the second derivative is related. So, and this is where it gets really interesting. Definition. This is the second definition of the same idea. So the graph of f is said to be concave up down if f prime is decreasing. Yeah. And concave up if f prime is increasing. Okay. Now, a very interesting question is to explain why these two definitions are equivalent. That means if you start with this definition, you can end up with this. And if you start with this definition, you can end up with this. That's a very interesting argument. Okay? But I won't talk about that. Instead, I'll make the connection between this definition and the theorem, which is perhaps easier to understand. If f double prime is continuous, then f is concave, so the graph of f is concave up. What order am I in? Concave down. If f double prime is negative, and concave up, if f double prime is negative. Positive. Okay? It's not very difficult to see why this definition implies this. If we think about the first corollary we wrote down today. If this function is decreasing, what can you say about the derivative of it? If a function is decreasing, then the derivative is negative. The derivative of whatever is under my hand, right? Okay. So, what's the derivative of this? F double prime, right? Does that make sense? Is supposed to be, you said it a second ago. Negative. Right? So, again, this thing is decreasing, its derivative is negative. Its derivative being f double prime. Okay, and that's what the theorem is saying. And similarly, this thing is increasing if its derivative is positive. Its derivative being f double prime being positive. Okay? So the relationship between this definition and this theorem is perhaps clear, and so I won't write a proof. But that's a pretty interesting relationship there. Okay, so let's apply that idea to this. We're looking for this special point so that we can determine the parts of this graph that are concave down and the parts of this graph that are concave up. So let's go ahead and find the second derivative. The first derivative is 3x squared minus 12. The second derivative is 6x. Okay? And it's not very hard to see where this is negative and where this is positive. When is this negative? Before 0, right? And when is it positive? After 0. Okay? So based on the theorem we just wrote down, the graph of f is concave down on negative infinity 0 and concave up on 0 infinity. It's worth, so let me draw the picture again. So this point was 0, right? This point was 2, this point was negative 2. And so in this region, the curve is concave down, and in this region, the curve is concave up. Okay, so perhaps it might be wise to give this point a name. What does that point mean? For us, it's the point where f double prime changes sign, right? Well, that point has a special name. If the graph, or let's say it like this, the point at which concavity changes is called an inflection point. And that's the special name we give that point, where concavity changes. And it could be changing from concave down to concave up, like in this picture here, or it could be the other way around. We don't distinguish between the two. If we have a change in concavity, then we name that point where the concavity change happens an inflection point. Okay, so now we're going to look at the second derivative test for local extrema. Like I said before, this word second is not doesn't imply that this is the second test, although it is. It just means that this test involves a second derivative. Okay? And it's a test for the same things. Okay? If you have a critical number and you want to see if it's a maximum or a minimum, the second derivative can help identify that. So we'll start by saying we want a function so that the second derivative is continuous on an open interval containing C. And already this test is more restrictive. You can't apply it, you can apply it to a smaller family of functions. Because if you remember the first derivative test, the condition was that f prime is continuous on an interval containing C, except possibly at C. Here you want the second derivative, which is harder to be continuous, on an interval containing C, including C. Okay? Anyhow, so let's see what it says. If f prime of C equals 0, okay? So that's got a horizontal tangent line there. And f double prime of C is positive of C is a local minimum. If f prime of C equals 0 and f double prime of C is negative, then f of C is a local maximum. If f prime of C equals 0 and f double prime of C also equals 0, then the test is inconclusive. Okay. Therefore, using the second derivative test, you can't, if the second derivative is 0, you still don't know anything about point C. It might be a max, it might be a min, it might be neither. The test doesn't tell you. Okay, the test tells you that f of C is a local max if the second derivative is negative, and a local min if the second derivative is positive. And here's a picture. Here's point C. You can see that the first derivative is equal to 0 because the tangent line is horizontal, and f double prime is positive because at C the curve is concave upward. Okay, so that f of C is a local minimum. For this picture, you have a curve where the tangent line is horizontal, so that the first derivative is 0, and the curve is concave downward. And those two things together tell you that at C you have a local maximum. Okay? Here's an example. Use the second derivative test to find the local extrema of f of x equals x cubed minus 12x minus 5. We already answered this question, but we use the first derivative test. We're going to come to the same conclusion with the second derivative test. So, local extremas, if they exist, happen only at critical numbers. So we're going to start by looking at where the critical numbers are. Calculate f prime. And so the two critical numbers that we get are -2 and 2. Okay? There are two types of critical numbers, where f prime is 0 and f prime doesn't exist. But these are the first kind. F prime of -2 equals 0, as you can see from the expression of f prime. And f prime of 2 equals 0. Now to apply the second derivative test, we need the second derivative. So f double prime 6x and the value of the second derivative at -2 is -12. More importantly, it's negative. And that tells you by the second derivative test that f of -2 is a local max. Okay? Similarly, the second derivative at 2 is 12, positive. Therefore, the test tells you that f of 2 is a local negative. So that's how we would use the second derivative test. It saves us a little bit of time if calculating the second derivative is easy. Because remember, to do this with the first derivative test, I have to think of a line, critical numbers, take test points, look at the signs, and depending on the sign changes, I decide if it's a local max or a min, if any. Okay, that could take a little more time But if calculating the second derivative is easy, this is a quicker way to decide if your critical numbers are indeed maxima, local maxima. But here's the thing. Let's look at the other function that we were studying just for a moment here. The other function we were studying was x to the 1/3 times x minus 4. And the derivative that we got was 4/3 x to the 1/3 minus x, 4/3 x to the minus 2/3. Right? And one of our critical numbers, one of them was 4. That's where the first derivative is 0. And the other critical number was 0. But f prime of 0 doesn't exist. Well, if f prime of 0 doesn't exist, I can't even use this test. You see what I mean? I can't, because I need f prime of that point to be 0. Here, f prime of 0 doesn't even exist. So I couldn't make the conclusion whether or not this critical number leads to a local max, local min, or neither. I couldn't tell. But that's not the only case where this test is weak. Here's another problem. Here. Consider this function. f of x equals x to the 4th. Okay? Now if you find f prime, you get 4x cubed. And so the only critical number you have is 0, at which point the first derivative is 0. Okay. So far, the second derivative is applicable. Now if you calculate the second derivative, you get 12x squared. And then you calculate the second derivative at 0, what do you get? 0. So the test is inconclusive. You can't make any conclusions about what happens at that critical number. But had you used the first derivative test, you would have seen that this critical number actually does lead to a local minimum value. In fact, the graph of x to the 4th is like a parabola. It's just a little flatter at the origin. So in fact, you do have a local minimum there. Okay, but the second derivative test doesn't tell you anything. Okay? All right. Now we're going to put everything we've learned together and start sketching curves for functions. Step 1 is the same as in any course you take in math. Whenever you're looking at functions, you have to start by identifying the domain. Okay? That in itself could be pretty complicated. Once you identify the domain, you want to calculate y prime, and from that, get your critical numbers, and perhaps from that, using the first derivative test, get your local extrema, find the intervals of increase and decrease, and then you calculate your second derivative, and then you count from there, you get your intervals where the function is concave up and concave down. You also get the points where concavity changes. We call those points inflection points. Okay? So you get all the information that calculus gives you in terms of derivatives. At step 3, you're looking for asymptotes, if any, and I want you to calculate the appropriate limits. Like I said before, it's not enough just to say that this line is an asymptote. Use the limits to identify why it's an asymptote. Step 4 is kind of optional, but if you can, if it's not too hard, find the intercepts. So you get a couple of points at least to see where the curve, a couple of points where that's on the curve, and of course sketch the curve. Okay. So we want to follow all these steps for sketching every curve. Here is an example. Let's sketch this one. F of x equals 1 plus x squared over 1 plus x squared. Quantity 1 plus x squared over 1 plus x squared. Okay. So, what's the domain of this function? All real numbers. Okay, so step 1 is done. Now we need the first derivative so we can get some critical numbers and other information. Here we're using the quotient rule. And it would be good to simplify. Okay? So maybe we can take out a factor of 2 times 1 plus x. I'll factor that out. Then we would have 1 plus x squared minus 1 plus x times x. And then simplifying a little more, we get 2 times 1 plus x. Now in the bracket we have 1 minus x. Because x squared cancels with the negative x squared there. Over 1 plus x squared squared. Okay? Is that clear? Now from there we can get the critical numbers. And first let's think about where the derivative is 0. Derivative is 0 at which points? Negative 1 and 1. F prime of x doesn't exist at which points? No, right? So that doesn't give you any critical numbers. So these are your only critical numbers. Now you can go ahead and go through the intervals and see where it's positive and negative, to change the sign and all that, to get the intervals of increase and decrease. But we're going to do similar sign analysis or variation of signs for the second derivative. Now I'm going to show you a table that's going to summarize all the information we need. But before we look at the sign changes of f prime, we want to look at f double prime, and then we'll do all that together. Okay? Let me write f prime again, a little nicer. This is f prime. Okay? It might be easier to calculate it this way, just so you don't do the product rule. So f double prime would be the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. here, so let's see if we can find some common factors.
1 plus x squared,
1 plus x squared,
4x.
4x, and that's it, right? So maybe with the negative, we can factor out negative 4x and 1 plus x squared. And then we're left with, from the first term, 1 plus x squared. This is gone, this becomes a plus. So we get plus 2 minus 2x squared over 1 plus x squared to the fourth. So now this cancels one of the factors in the denominator. So we have x squared cubed. Within we have a negative 4, and then within the bracket we have that's a 3 minus x squared.
Okay. 4x, no?
4x, yeah. Thank you. All right. Does that make sense? All right. And remember that we're trying to study the sign changes of f double prime, so it might be wise to see where f double prime is 0. Where is f double prime equal to 0? When x is 0, and when would this factor be 0? Square root of 3 and negative square root of 3, right? And then also where f double prime does not exist. Is there such a point?
No.
Okay. Great, so what we have is, these are important points for us, because if these happen to be sign changes for f double prime, that will tell us something about concavity. And also if there are sign changes, we call these inflection points. And then these points are important so that we can study the sign changes of f prime, which will in turn give us the intervals of increase, decrease, and local extrema. So now what we'd like to do is set up a table that handles all the possible cases for the signs of f prime and f double prime. Okay? So let's move here. This table is called a table of variations. Anyways, it's a direct translation from French. I don't know what's probably table of variations, table of sign variations really would mean. And in this table, the first row, kind of, the first line, is really the x-axis. Okay? Now, then we have, let's do it this way. Then we have some sign changes for f prime. Then we have some signs for f double prime. And then from looking at these two, we'll make a conclusion about what f looks like. But consider this first line as the real line, the x-axis. And although I'm going to put a line here, just for stylistic reasons, this is just the real line. It continues indefinitely in both directions. As a matter of fact, we could put plus infinity here and minus infinity here. Okay, is that clear? Now the important points that go on the x-axis are critical numbers and the points at which f double prime is 0. So we want negative 1, 1, 0, negative rad 3, and rad 3. Of course, in order. So 0 is here, negative 1 is here, and negative rad 3 is here, and rad 3 is here. No, this is 1. Here's 1. Okay, we have many regions now that the x-axis is divided into. Okay? And we could draw some vertical lines to separate those regions. Now, in this first two rows, we're just going to put signs. We're going to talk about the signs of f prime and f double prime. Okay? Now, we'll start by looking at these critical numbers here, because that's all we need for f prime. The others are there for f double prime. So as far as f prime is concerned, we're looking at -1 and 1. What do you know about f prime when x is -1? What is the value of f prime?
0.
0. So I'm going to put a little 0 here. Okay? I'm going to put a little 0 here. So if there were to be any sign changes, they wouldn't happen in this interval, or after 1. Therefore, we just need a 1 test value before -1. That'll take care of it. So pick a test value before -1, any number. -2. Now go to f prime, which is here, and look at the sign of f prime when x is -2. If x is -2, this is 4. 1 minus 4 is negative. The rest is positive. So then we have negative before -1. Okay? Do something similar. Take a test point between -1 and 1. 0 is a good test point. Okay, and you'll see that f prime is positive. And then if you pick a test point after 1, you'll see that your f prime is negative again. Yes? So as far as f is concerned, what can you say about f in this box over here, based on the sign of f prime? That's decreasing. And here also. And that here it's increasing, decreasing, and decreasing. Yes? Okay. Now let's look at f double prime. If there were to be sign changes, they would only happen at -rad3, at 0, and at rad3. So for the purposes of calculating f double prime, you could ignore these other 2 points, -1 and 1. So now, take a test point before -3 so we can handle this box here. Negative square root of 3 is -1.7, about 1.7. Take -2. And then use this expression over here for f double prime. If x is -2, this part is positive. And this would be 4. 3 minus 4 is negative. So you get positive times negative. It's negative. Okay? So then you can come here and say, okay, this is negative. And then you can take a test value between negative square root of 3 and 0. Again, -1 doesn't play any role for f double prime. Okay? If you take any test value between -rad3 and 0, you'll see that it's positive. F double prime, that is. So in these two boxes, you have positive. Okay? And then you'll have negatives here and positive afterwards. Okay? You can take test values to verify those. Anyhow, more importantly, what does f double prime negative tell us about the graph of f? Concave down. And here it's concave down. Here it's concave up. Okay. Now combine the fact that in this region you have to be concave down and decreasing. Based on those two, what part of this end curve do you take? The right side. Yes? Because if you took the left side, you're decreasing. So combining the fact that you're concave down and you're decreasing, you take this shape. Alright? And if you're decreasing and concave down, this should be concave up, sorry. There you go. Then the curve would be this shape. And then the curve would be this shape. And then this shape. And this shape. And then this shape. Okay? So these are the pieces of the curves. Yes? Are you with me?
Yeah.
Okay. Let's go back to this -1 and 1 business. Look at f prime near -1, what happens to the sign change? From negative to positive. So what can you say about the graph of f at -1? Local minimum, right? Therefore, over here, you have a local minimum. And now let's look at 1. What can you say about the graph at 1? F prime changes from positive to negative, so the graph has a local maximum. Okay, now let's look at the other important points, and these are for f double prime. At negative square root of 3, f double prime changes sign. What is that point called?
Inflection point.
Inflection point. So here we have an inflection point. As a matter of fact, 0 is an inflection point as well. And so is positive square root of 3. So when we're talking about the intervals of increase or decrease, it's all here. This table actually answers all the questions you might be asked about how the function, how the graph of the function looks. So even if you didn't have to sketch the curve now, you could very easily tell someone where the function increases. You just have to look here. And then decide that f increases between -1 and 1 and decreases everywhere else. Okay? You could also identify the regions where the graph is concave upwards. And that's the region between negative square root of 3 and 0, because f double prime is positive, and the region where x is more than the square root of 3. And that everywhere else the graph is concave downwards. Okay? All right. Those points we highlighted as being local extrema or inflection points are important. We have the x values at those points. Let's see if we could work out the y values. The first point is f of negative square root of 3. Okay, so if you plug this into the function, you get 1 minus square root of 3 squared over 1 plus 3. So we get 1 minus square root of 3 over 4 squared. Okay? So maybe we can work that out. So you get 4 minus 2 square root of 3 over 4. And that gives you 2 minus square root of 3 over 2. Okay? And if you work out f of positive square root of 3, or maybe f of 0, that's 1 plus 0 squared over 1 plus 0. It's just 1. And the y value at square root of 3, I think the calculations are very similar. You end up getting 2 plus square root of 3 over 2. I mean, to the calculations of f of negative 2. And let's calculate the y values at the other point. So f of negative 1. That's 0. And f of 1. Is 2. Right? Okay. Is that clear? Or wrong? Here? Here? Oh, I don't know, it might be wrong. Let's work it out. 1 minus square root of 3 is squared is 1 squared minus twice the product of these two plus square root of 3 squared is 3. This is 1 plus 3 is 4. Yeah. Alright, so what did we just do? We calculated the y values at those important points. Okay, so The last step was to calculate intercepts. The last step was to calculate, and let's look at the function again. F of x equals 1 plus x squared and 1 plus x squared. So the y-intercept, there could only be one y-intercept, and we already found it. It's right here. F of 0 equals 1. There can't be more than one y-intercept, right? Otherwise it won't be a function. So the y-intercept is already found. 0, 1. It also happens to be a point of inflection. To get the x-intercept, you set the function value to 0, and it turns out that x has to be negative 1. There's no other way this function could be 0. As a matter of fact, we found out that that was a local minimum. That was one of our points. So finding these intercepts doesn't add much value in this particular problem, but nevertheless, we know that at least there are no other x-intercepts. Okay. How about asymptotes? Well, are there any vertical asymptotes? No. I mean, if your domain is all real numbers, then there can't be any vertical asymptotes. But let's look at horizontal asymptotes. How do you look for them? You calculate the limit as x goes to infinity, right? Of the function. Now it will be easier to write the function in expanded form. And after some calculations, you see that this limit is what? 1. As a matter of fact, if x is going to plus or minus infinity, this limit is 1. So y equals 1 is a horizontal asymptote. Near x positive or negative infinity. In other words, on the far left and the far right, the graph is approaching this horizontal line. Okay? Great, so let's put things together. We might need some approximations here. Square root of 3 is about 1.7. 2 minus 1.7 is 0.3. Divided by 2 is about 0.15. Okay? So it's a positive number, a small positive number. And again, this is about 3.7 divided by 2, so it's about 1.52. Okay? So we can put them on the graph. So here we go. We will put the key points here. So we'll put 0, 1. And then negative 1, 0. And then at negative square root of 3. So if this is negative 2, negative square root of 3 is about here somewhere. And the y value is really small. It's about here. Okay? And then at positive, and then at 1, if x is 1, what is y? 2. Yes? Do you know where I'm looking when I look on that side?
No.
Oh, okay. F of 1 is 2. Those are the calculations. And so then if x is positive square root of 3, which is about here, the y value is about 1.5. It's about here somewhere. Okay? Furthermore, we have an asymptote at y equals 1. Now these points that I put on the board describe the regions on the x-axis for which those curves at the bottom of the table have to be drawn appropriately. So in other words, before negative square root of 3, you have to draw that shape. Here's negative square root of 3. Before that, this is the shape you have. And because we said that we have an asymptote, we actually know what happens as we go further left. Is that clear? And then between negative square root of 3 and negative 1, we know the shape looks like this, right? But I have to, until negative 1, so I'm kind of forced to draw the picture that way. And then between negative 1 and 0, it's increasing and concave up. And then between 0 and 1, it's increasing still, but this time it's concave downwards. Okay? Here the slope is 0, here the slope is 0. We identified that, so make sure that the graph has a horizontal tangent there, and here. Anyhow, between 1 and square root of 3, it's decreasing and concave down. After square root of 3, it's decreasing and concave up. And as you continue, you know that you have to be asymptotic to the graph of y equals to 1. Okay? So here you can clearly see your local extrema and your 3 points of inflection at which concavity changes. All right? Any questions? Yes?
There's no vertical asymptote.
Because the domain was all real numbers. When you have a vertical asymptote, it's basic. One of the things it means is that x can't be that value. Okay, but if x can be any value, then there can't be any vertical asymptote. More practically, because the denominator is never 0.